Okay guys, next we are going to talk about the functional calculus. It's kind of sophisticated topic, but it is just an introduction. Okay, look at here. You suppose that we have a complex valued function of a complex variable z. Okay, it means f is defined from a subset of complex number into complex number, you can see. And this is the domain of f. Okay, so you are given this function, a complex valued function of a complex variable z. Now look at here, let's say t is a bundle linear operator on a Hilbert space H. Okay, our goal here is to define an operator f of t belongs to b of h. Look at here, like f is a function of a complex variable, right? So f of z is a complex number. Now we want to know how we can define f of t to be an operator, to be a bundle linear operator on H. Okay, here you can see f is a function of the argument z and the value is a complex number, but here we want to define f of t. It means the argument here is the argument is an operator, okay, and then f of t must be, it means the value of f of t must be an operator. Okay, we are going to see that how we can define or how we can do this. You can see I said meaningfully, and you can read here. Let me later about this meaningfully, and this sentence I will explain later more. What does it mean, meaningfully, which we want it to be a natural extension of function f from complex argument to operator argument. Okay, let's start with this, maybe the simplest case or example. Look at here, what do you see here? F of z, z is a polynomial, okay? It's a polynomial with complex coefficients, okay? With complex coefficients alpha I, okay? How can we define f of t? Okay, in this case it's quite easy. We define f of t to be, look at here, here when we say alpha z, this means alpha z times 1, right? Here 1 or identity means identity operator. So we can define f of t to be alpha 0 I plus alpha 1 t alpha 2 t2, okay, up to alpha and tn. Tn means the product of t with itself n times, it means composition. So you agree with me, each one is an operator, so this makes sense, right? This makes sense. So the sum of these n plus 1 operators definitely is an operator here. So you can see f of t in this case makes sense. Another example is, look at here, if f from complex number into complex number, okay, is a holomorphic function on C. I don't know, I mean, if you are familiar with this notation of the holomorphic function from complex analysis or not, I'm not sure, but quickly it means when we say a function is holomorphic, it means this function at the neighborhood of every point, is differentiable, okay? And then this function has a infinite power series or Maclaurin series, and the Maclaurin series of this function, let's say, is f of z equals sigma alpha n zn. Okay, now how can we define the f of t to be an operator, okay, using f? This is our function. How can we define f of t to be a bundle linear operator on H? You can see I said in this case we can define f of t to be, look at here, this sigma alpha n tn. You can see this is an infinite series. Okay, if you look at the sequence of partial sums of this series, okay, actually the sequence of partial sum of the series is a sequence in B of H. right? Because when we say partial sum, it means alpha n, Tn, n from 0 to k. So the sequence of partial sums of this series is a sequence in B of h, okay? And that sequence is conversion, okay? It's conversion. Conversion in B of h, because it's a complete space. Okay, it's conversion to an element of B of h, which is an operator, and defined to be f of t. But of course, you may wonder, why is this series conversion? Okay, I leave it to you as an exercise to figure out. But do not worry. I mean, if you are not familiar with this discussion from complex analysis, you don't have to figure out. Okay, you just bear in mind that in this case, this is how we define f of t. Okay. In particular, look at here this very interesting example here. F of z equals exponential z, exponential function. We define f of t, of course, we denote by exponential t, e to the power of t. But what does it mean? This is how we define this, okay? How we define. And if you wonder why, let me remind you about the Maclaurin series of exponential function, which is very well known. Okay, let me remind you about the Maclaurin series of this function. If you remember here, the exponential z, okay, the Maclaurin series of this function is this, sigma 1 over n factorial zn, which means this, right? Okay, so using the Maclaurin series of this function, actually this is a particular case or particular example of this one. We can define f of t, it means exponential t is defined to be sigma 1 over n factorial tn. Look at here, just like this. You just follow the Maclaurin series. And this means actually, when n is 0, okay, this is 1 and t to the power of 0 is defined to be identity operator. And t plus 1 over 2 factorial t2 and so on. And if you look at the sequence of partial sums, for example, the first 4 terms, okay, like up to here, the sequence of the partial sums of this series is a sequence in B of h. For example, when you say 1 plus t plus 1 over 2 factorial t2, like look at this partial sum, definitely is an operator on in B of h, right? So this is conversion. This series, we can show that this is conversion to an operator, and that operator is defined to be exponential of t. Okay, another example here, if you have a function like f of z equals z bar, it means the conjugate of z. Yes, f of t is defined to be t star, the adjoint of t. Okay, so you can see, I mean, so far we have seen a few examples, like we could define f of t like with almost no problem and no condition. Now here's the question. You can see, let me read for you. We said, when can we define f of t in a meaningful way for more general functions, okay, for more general functions, f such that f of t behaves as we would expect f to behave. What does it mean? Look at here, so far we have seen a few examples, right? But the question is, can we define f of t for every kind of function? And if we can do this, do we need some condition? Of course we need. We are going to talk about it. But look at here, what does it mean this? For example, we have a function f of z equals the square root of z, and we know that the square root of z square equals z. Now, if if we define the root of t to be an operator in B of h, okay, if we define it, okay, if we define the square root of t to be an operator, so of course we expect the square root of t behaves just like this, okay, It means we want the square root of t, the square root of t squared to be equal to t. Okay, so you can see. Of course, to do this, we need some condition actually. When we are going to define this f of t for more general functions, such that it has the same property as the function that we have in calculus, of course, we need to consider some condition. You can see, I said we require following two conditions. Let me read for you. First, f must be defined and continuous on the spectrum of t. Okay, this is the first condition. It means the function f must be defined on the spectrum of the operator t. It means if you want to define f for a bundled linear operator f of t, we need two conditions. F must be defined on the spectrum of t, and f must be continuous. And the other one is the operator t must be normal. Okay, you may wonder why we consider these two conditions. I'm going to explain you by some simple examples, like why we are considering these two conditions to define f of t for more general functions. Okay, look at here. We have a function f of z equals 1 over z minus lambda. Lambda is a fixed complex scalar. And this function can be written as z minus lambda to the power of minus 1. This means the inverse, multiplicative inverse. Okay, for sure you agree. Okay, I'm sure you agree with me that the function f is not defined on lambda, right? Z cannot take the value of lambda because 1 over 0 division by 0 is not defined. Okay, now look at here. So the function f is not defined on lambda. It is defined at every complex number except lambda. Okay, now look at here. If we follow the formula of f, let's say t is a bundled linear operator, okay, and we define f of t to be, look at here we have z minus lambda, but lambda means lambda times 1. So I can define f of t minus lambda times I, identity operator, inverse. Okay, we can define it like this. But here's the problem. If lambda belongs to the spectrum of t, right, f is not defined on lambda. Okay, and here is the problem. Look at here. When lambda belongs to the spectrum of t, t minus lambda I is not invertible. So this definition doesn't make sense. Let me put it all together. So the function, okay, lambda belongs to the spectrum. The function f is not defined on lambda. So it means the function is not defined to a spectrum of t. So that's why you cannot define f of t. Because when you try to define f of t, like just follow this formula, you say f of t equals t minus lambda I inverse. But lambda belongs to a spectrum, so t minus lambda I is not invertible. So this inverse does not exist. So you cannot define f of t. Why? Because f is not defined on lambda, which is an element of the spectrum. So it means f is not defined on a spectrum. So this is an example about this, why we consider this. And another example, why do we consider t to be a normal operator? When we say normal operator, it means t commutes with this adjoint. Do you remember? t star equals t star t. Okay. First of all, okay, why do we consider this? Let me give you an example of finite dimensional space. Okay. Do you remember that if we are talking about the bundled linear operator on finite dimensional space, let's say n-dimensional Hilbert space, we are simply talking about actually matrices or matrix algebra. Every bundled linear operator like T corresponds to a matrix like A, right? We talk about this. So when you say I want to define f of t, it means you want to define f of A. It means if we have a function like here, like f of z in general, if you want to define f of t for a bundled linear operator on finite dimensional space, every bundled linear operator on finite dimensional space corresponds to a matrix. So when you say I want to define f of t, it means you want to define f of A. Okay. It means f to define f for a matrix. Okay. Let me recall you this from the linear algebra. A matrix, okay, a squared matrix, n by n matrix like A, is called diagonalizable, okay, diagonalizable, if it can be written in this form: A equals U d U inverse. Here, U is an invertible matrix, okay, U is an invertible matrix, and this means the inverse of U. And D is a diagonal matrix, okay. I'm sure that you know about what it means by diagonal matrix. Okay. And look at this. So this is the definition. We say A is diagonalizable if A can be written in this form. Now, okay, now look at here. We have this well-known fact from linear algebra that if A is a normal matrix, then then it is, sorry, here is a typo, then it is automatically diagonalizable, okay. But what does it mean when we say A is a normal matrix? Okay, look at here. It means A commutes with its adjoint. How do we define A star? Do you remember A star? The adjoint of a matrix, right? It's defined to be the what was that? The conjugate complex transpose, right? Conjugate transpose of the matrix A. Do you remember? We defined earlier. So when we say A is normal, it means A commutes with its adjoint. Okay, A star A equals A star, and A star is the adjoint of A, and is defined to be the complex conjugate transpose of A. Okay, and look at here. In particular, if we have a matrix, okay, a square matrix by real entries, okay, real entries. Okay, what we mentioned here in general was for any square matrix with complex entries. Now, in particular, if we have a square matrix with real entries, okay, then every symmetric matrix is self-adjoint and definitely normal. Why is it like that? Again, let me explain you here. Look at here. If we have a matrix, a square matrix with real entries, right? Okay. When we say A is symmetric, what does it mean? It means A equals the transpose of A, okay? But actually the transpose of A equals the adjoint of A star, okay? So it means A equals A star. So what does it mean? It means A is self-adjoint. So definitely when A is self-adjoint, it can commute with its then we have this actually. It means when A equals A star, A commutes with A star. So definitely A is normal. Look at here. For example, look at this matrix. Do you agree with me? This matrix is symmetric because the transpose of this matrix is a matrix 2 by 2 matrix. The transpose of this matrix, which is this, equals itself. But after transpose, if we take complex conjugate of each entries, which means we are going to find A star, the adjoint of A. Look at here. Since each entry is a real number, so this equals this. So what is it? A equals A transpose, and or the transpose of A, and this equals A star actually. And you can see if A equals A star, it means A is self-adjoint matrix, definitely normal. Okay, so